So today we're going to look at the tangent line problem. It's the definition of the derivative and one of the most important problems in the development of calculus. So let's look first at the graph I've got put up here, and then we'll start working out the problem. The red curve is the function f of x equals x squared. The green line is an arbitrary line drawn through it that intersects a curve in two places. The lower place I've labeled as x f of x. The upper place is labeled as x plus delta x, f of x plus delta x, where delta x is just this change across the graph as you've gone up the curve, the change in the x direction going out horizontally. Now, if we think about it, we can find the slope of this green line. It's known as the secant line, and its slope is just f of x plus delta x minus f of x over x plus delta x minus x, which is our difference quotient. So let's write that out, that the slope of the line is equal to f of x plus delta x minus f of x over x plus delta x minus x. You'll see that this x and this x will cancel with one another. So now let's simplify it. Since we know f of x is x squared, we can say that the slope is equal to x plus delta x squared, because we just plug that in for f of x, minus f of x, which is x squared, all over delta x. So that's the slope of this line that's intersecting at a second point. But we're seeking to have a tangent line that intersects at only one point, which is the point of tangency as we've defined it. So we're looking for a line like this that's just intersecting at that one point, x f of x. To get that, we can take the limit as delta x approaches 0 of this equation for slope. Because if you think about it, as delta x is approaching 0, we're moving the second point down the curve, and it progressively moves down this curve until delta x is 0, and it's just tangent touching there at x f of x. So we'll have the limit as delta x approaches 0 of x plus delta x squared minus x squared, all divided by delta x. Now, to evaluate this limit, we can't just plug delta x in because that would make the denominator 0. So we need to try to cancel a factor or rationalize the denominator to get delta x out. So first, let's FOIL out x plus delta x squared. So by doing that, then that becomes the limit as delta x approaches 0 of x squared minus or plus 2x delta x plus delta x squared minus x squared, which was the second term here, and all of that's still divided by delta x. Notice this x squared and this x squared cancel one another. Then we can factor delta x out of the numerator. So we get the limit as delta x approaches 0 of delta x times 2x plus delta x, just factoring a delta x out of our numerator, all over delta x. We can then cancel these delta x's, and we're left with just this numerator. So when we take the limit, this delta x goes to 0, and we're left with simply 2x, which is the derivative of x squared. So if we think about what that means on the graph, we're coming down here, we're coming down this curve, we're coming down this curve. When delta x is 0, we're at this line. The line is tangent at the point x, and the slope of the line is 2x. Therefore, we've proven the derivative that at any point on this curve, f of x equals x squared, if we plug in the x value into this derivative, which is 2x, we will get the slope of the line to represent the slope on the curve at any given point.